terms of that architectural modeling, we saw some people nodding their heads that architectural modeling goes on at the same time as RTL. Emulation is a great way to test that a product meets performance, because emulation is obviously cycle accurate. If you prove that something's true in emulation, then you've proven it's true for the silicon as well. But oftentimes an architectural model is in some high-level language, or maybe even a mathematical package like MathCAD. So by a show of hands, are people doing C modeling of their products before? Okay, a smaller part of the crowd, maybe 12%. And then any other tools like MathCAD or mathematical models at a higher level? Got some of that going on. All right, and then who is doing emulation? Okay, not as many as I would have thought. So when you have a C model in particular that is being used for architectural testing, the RTL often cannot be run for enough cycles to prove that the architecture is satisfying requirements. And so what you need to look for is a sense of transitive correctness. So I've tested the C, and I know the C is equal to the RTL, and so I know the RTL satisfies requirements. And one way to achieve a transitive correctness is to create a C model that has properties of that it can be cycle accurate when it's working with the RTL for comparison purposes, but it can run into discrete event mode, not simulate every cycle when it's running alone. And the reason that's so important is that if you want to run 1 million cycles, you can't simulate every cycle necessarily. And so this is one way in which you can create those models and create that transitive correctness. And then to say that the C is equal to the RTL, well, that's tricky. There are some companies that offer, I believe, tools that will say that some system C is equivalent to some RTL, but that's a very particular system C that is effectively already RTL. And so a lighter weight approach that maybe is not 100% confidence, but is pretty good confidence, is just to have dual code coverage. You run the two models together long enough to know that all code paths on the C have been exercised and all code paths on the Verilog have been exercised. And so if all code has been exercised and if the two models have not diverged from each other, then you can be comfortable that your RTL is satisfying your requirements. And so basically the rest of this talk can be summed up by this three-phase testing pipeline. To leverage the corporate resources of hundreds of CPUs, maybe thousands of CPUs, depending on where you are, tests need to be generated at a very high rate of speed. There needs to be a launch technology that will automatically launch tests into the farm, keep the farm busy, keep the CPU farm busy. And then the results need to be brought back and presented to the user in a way that a small number of users can handle thousands of tests, maybe more, and not become overwhelmed. And that's especially important when the tests aren't doing so well, when there are some failures to be considered. And so by amplifying, to use CPUs instead of people, you need these layers of technology to facilitate the work. So the red, green, and blue from the slide are going to move down into the lower corner now. And so we're going to know what section of that phase we're talking about on each slide from here out. And so the game-changing technology that we think makes a big difference is SQL, applying an SQL database. And it can be done piecewise. It doesn't have to be done all at once. So test results, for example. If you go no further than storing which test was run, the seed that was used, and the pass-fail result, you've already changed the rules on what's happening in your design and verification effort, because there's so much information that can be mined from that. We can track failures, the history of how a test is done, if a test is failing now when it wasn't. If a test is failing on 40% of seeds now, and it was failing on 60% of seeds before, we can watch that test devalue. So just storing those three things on a regression process is going to make a huge difference in your environment. Storing test lists in the database. This is also a key technology. It's not very difficult. Test lists tend to be pretty simple, lists of test names or of test numbers. By putting them in the database and by knowing that you're going to evolve that test list over time, a lot of value can be added, and the value of each test can be managed over time. And then finally, and this is a big one, it's a little bit harder, but it's definitely doable, to store your actual test descriptions in a database. And this is where, when you get all three going, this is where some of the really high leverage techniques can be employed. And that's what we'll talk about later. So a few words of warning. We've talked about C models, and we've talked about SQL. By no means, never cross the streams. You don't want to try to do direct SQL put and get from C. It's too laborious. So employ some type of database package. Don't be doing the string manipulation necessary to communicate with an SQL engine without a built-in library. It impedes creativity. All of the benefits that come about from being able to be more productive are taken away again by being focused on what you've already implemented, what you can support versus what you haven't implemented yet. And so focusing on the first part of the testing pipeline, where you're going to generate tests as quickly as you can. Obviously, one of the most common ways to generate different test scenarios quickly is with constrained random generation. And I think that's what, is it true? Is that what most people use, constrained random generation? Yeah, so then now we've finally a question where the majority says yes. And constrained random generation has been a real benefit to the industry over the past 10 years. Where it's getting a little complicated these days, and Paul Tobin put this out as one of the things we should talk about at a recent DV Club event, is in knowing how the constraints are working together. So has anyone doing any type of constraint coverage where they're looking at how their constraints are being covered? Yes. Okay, some people actually do. Can we talk about that sometime? So that's a big one. So knowing how your constraints are recovered. So the database approach is actually a little different. It's different than constrained random because the test at execution time is not as randomized. There's not as much up to randomization at execution time. So for example, if you take what can be randomized as stuff that might be randomized prior to time zero or at time zero versus what's randomized during the simulation, the tests that you upload to the database, maybe you're going to want to upload post initial randomization and upload basically what is a particular functional coverage point. Upload that to the database. And then let a little bit more randomization go on with time. And so, for example, what we had employed on the QoS network processor was to create a set of small programs that took that initial test population that we got from our marketing folks and from our QA engineers, take that initial test population and begin smearing coverage around different dimensions. So to sweep through various functional coverage parameters. And then there are some heuristics you can do too when coverage assertions are applied and you can see which coverage bits are being hit versus which aren't being hit. The test is fixed functional coverage. The functional coverage is not randomized when the test runs. So you can take that test and begin applying small mutations to parameters of that test, and it's relatively likely that you can create a test that falls into a neighboring coverage bin. And so when your tests are stored as data, you can start writing programs on them. It's a lot like constrained random generation, but all that randomization is prior to test upload, and then the test, once it's uploaded, is used as is for execution. And you're creating more tests all the time, so it's not necessarily that the test being less random is ever implies less coverage. And so when you store your tests in a database over many years, you start to learn lessons about how that test population grew. And this is a bit like coverage, constraint coverage. Looking back on a database of 100,000 tests, you start to notice similarities that were not necessarily intended. And this is because a test ends up having many children, especially a test that entered into a unique coverage point and then became the father or the grandfather for all the other tests in that coverage neighborhood. It's a little bit like inbreeding. It wasn't, you don't necessarily want your tests to resemble each other in 90% of their DNA. And so one way to try to limit that would be to just track how much influence any one test has. Somebody we were talking to also said a test shouldn't live for too long. If after some number of months of being used, some number of weeks of being used, you replace a test with a test of equal coverage, then that's another way to overcome this snowball effect. These optimizations are only possible, this analysis is only possible of your test population when functional coverage is persistent, when it's stored. If you run a regression and you look at what the functional coverage was on that regression, but then that's forgotten, it's not necessarily the case that you can know that coverage is getting more broad or that your test population is getting more diverse over time. So still in the test generation category, Another category, another way to generate tests is testing with feedback. Now, this is particularly useful in tests that have a non-pass-fail output. So quality of service is an example, electrical compliance for analog mixed signal testing. But when there's an output that comes out of the test that's a number, first of all, that represents a problem in some teams, because when you say, yeah, we ran the test and it gave us a 3% error, you're just like, well, does that pass or does that fail? Well, sometimes you don't know. But if you take that test and run it through a feedback loop where you mutate the test slightly and try to amplify that error, well, then if you can turn a 3% error into a 10% error, well, now that is objectively an error that needs to be fixed. And this can be applied to different types of technologies, but this is, again, only possible if both your results are stored somewhere as a data structure and your test, your basic test description, is stored as a data structure. When those two things are a data structure that can be acted on by a program, they can start being used in a feedback loop, in an optimization program, to create more effective tests, more pointed tests. And this can be used to make a test shorter. I guess they're not around anymore, so I can say when I was at Seaport, we used genetic algorithms to filter down a post-silicon DV scenario to something that could be recreated in an RTL environment. These types of treating tests as data is very, very powerful.